Hello, and welcome to Agrosive Physics. Today is day 100, and what I'd like to talk about today is the electromagnetic spectrum. Now, on our reference table, we have the electromagnetic spectrum listed horizontally, and what that lists is all the different forms of light. Now, remember, although these act differently, they are all forms of light, so they travel at the same speed. When they're in a vacuum, they travel at 3 times 10 to the 8 meters per second, and when they travel in dispersive materials, they travel at slower materials. So as soon as you get into a more dense object, such as air, such as water, such as glass, such as plastic, they're going to slow down. Now, if we have dispersive materials, they may have different index of refractions and change speed differently. So the frequencies will determine how fast they travel in dispersive materials. Now, some of the things to note about the electromagnetic spectrum is that it is listed horizontally, and it goes from gamma radiation to X-rays, ultraviolet to visible, infrared to microwave, down to radio wave. And these also show on the top you have wavelengths, and on the bottom you're listed in the frequencies. So you'll see that at the top you're going from 10 to the negative 13 meters for gamma radiation, all the way up to 10 to the 4 meters, which is 10,000 meters for long radio waves. On the bottom, gamma radiation is around 10 to the 22 or so, and radio waves can be in terms of the frequency, and then radio waves can be 10 to the 5 hertz in terms of frequency. So as one gets bigger, the other gets smaller. So the wavelength is getting bigger, and the frequency is getting smaller as we go from left to right. Another thing I want you to note is that each of the bands does not have a clear distinction of where it starts and where it ends. There's a lot of overlap in the electromagnetic spectrum. If you think about a rainbow, it's hard to denote where the red starts and the orange begins because there's an overlap. There's a blending between the different colors. All the different forms of light act the same way. So the electromagnetic spectrum chart is useful for getting general values for the frequency and wavelength, but not specific values. You'll also notice that there is the visible light spectrum listed as almost a cutout. It expands it so you can read some of the values. Now on the chart, it goes from violet to red. Normally we list the rainbow as red, orange, yellow, green, blue, indigo, and violet. Now on this chart, there's no indigo. And that's because we break the different frequencies of light into general slices that are about the same size. And since we're going from frequency values from left to right that go from bigger to smaller, that's why violet is on the left and red is on the right. So the frequencies of light decrease as we go to the right, but that means the wavelengths increase. So red has the biggest wavelength of light and violet has the smallest wavelength. Now typically our values for wavelength is around 750 nanometers to 400 nanometers for red being 750 to violet being 400. And from the chart, you can read the values for frequencies. Red is around 3.84 times 10 to the 14 hertz, and violet is around 7.69 times 10 to the 14 hertz. It's not a huge discrepancy, but if you think about it, that's how we see every object that we're able to see with our eyes. So it's a small part of the electromagnetic spectrum, but it is very important for us as humans. If we look at the sun is producing all the different forms of light, and the different wavelengths and frequencies can be viewed differently. Of course, we can only see the visible spectrum, but if we use filters, we can view the sunlight using those different filters. And what I have is a slide that shows the different filters. Now, of course, we need to shift those into the visible spectrum, but that gives us a general visual representation of what the different wavelengths look like using different filters. Visible light is the most boring. It's all the forms of light, so it is just white. So in space, you would see the sun as just a white ball of light. Now that being said, just to recap, all the different forms of light overlap. Not all together, but gamma overlaps ultraviolet X-rays, and X-rays overlap ultraviolet, and then you have infrared overlapping microwave, and microwave overlaps some radio waves. There's no clear-cut distinction between the bands. You could have an X-ray and a gamma ray at the same time, and depending upon its characteristics, it may be considered one or the other. Now, It's important to realize that the different forms of light affect us humans differently. Microwaves can cause water to vibrate rapidly because it has the same natural frequency. So microwaves would be bad for us if they hit it. However, visible light hits us and we're fine. If ultraviolet light hits us, it could cause pigmentation in our skin to change colors. We can get burned from the ultraviolet light. If we stand on the other side of glass, we will not get sunburn. We might get hot, but we're not going to get sunburn because ultraviolet light is actually blocked by glass. So if you're driving in a car and you have your arm out the window, your arm may get burned, but your face isn't going to get burned necessarily through the windshield. So different forms of light affect humans differently and affect different objects differently. If you think about X-rays, it can penetrate our skin, and then we're able to see internally our bone structure. So X-rays, microwaves, infrared, ultraviolet, all these different forms of light have different effects on our bodies. We're constantly being bombarded by radio waves that have no effect on us. Visible light has no effect on us. If we get hit by gamma radiation, we turn into the Incredible Hulk. So these are all different forms of light, and they affect us in different ways. Now, the disclaimer, of course, is we cannot actually turn into the Incredible Hulk, no matter how much we wish that were true. Gamma radiation will cause quite a lot of damage on us and damage our skin and our cells quite rapidly. So, electromagnetic spectrum. These are all forms of light. They can all travel through space. There's no clear-cut distinction. Our chart lists the electromagnetic spectrum in terms of wavelength that increases and frequency that decreases. And as you know, the difference between the wavelength and frequency is indirect. As the wavelength goes up, the frequency goes down. As far as the electromagnetic spectrum goes, if you're asked questions that you don't know a specific value for, remember that we do have a chart in our reference table for not only the electromagnetic spectrum, but also for the different values for the index of refractions. And if there's an equation you don't know, there is an entire section that's denoted for the waves part of the course. So we have waves and light in its own section. So you should be able to find any equations that you need or any values that you may need from that chart. A lot of this section is conceptual. However, the Snell's law, index of refraction, N equals C over V, and possibly critical angle are things you may have to calculate. But as far as light goes, this should be just about the end of this unit. We'll move on to other topics from here. But today was day 100, and I thank you for your continued support and watching all these videos through. We have 44 to go, and we should be done with our introductory physics course. So happy 100, and I thank you.